Hi everybody. In the past few videos, we've been solving the Schrödinger equation for certain model systems in quantum mechanics. The particle in a box, which tells us about translational motion, and the harmonic oscillator, which tells us about vibrational motion. In this video, we'll be focusing on rotational motion, objects moving around circles and on the surfaces of spheres. These are really our last model systems before we fully move on to atoms. Let's define the context in which we're trying to solve the Schrödinger equation here. Like the particle in a box, we're looking at an object that's moving along paths of constant potential energy. We'll define the potential energy operator as V equals 0. But unlike the particle in a box, in which the object was moving in a straight line, the object's motion is now confined to circles and the surfaces of spheres. It's important for us to look at these systems for two main reasons. First of all, as we'll see in the next video, rotational motion has implications for spectroscopy. It's possible to see the quantized energy levels of a rotating object both in microwave spectroscopy and in the spacing of peaks in infrared spectroscopy. And maybe more important to what we'll learn going forward, the solutions to the Schrödinger equation for rotational motion actually tell us a lot about the angular part of atomic orbitals. We'll start by looking at the motion of a particle on a ring, an object moving around a circle of fixed radius r. Throughout this course, when we're looking at circles and spheres, it's often convenient for us to use polar or spherical coordinates. As you may remember, the polar coordinates r and phi relate to the Cartesian coordinates x and y by the equations shown on the slide. X equals r cosine phi and y equals r sine phi. In the Schrödinger equation, the kinetic energy operator includes the Laplacian operator, the sum of partial second derivatives with respect to x and y. If we want to work with polar coordinates, we have to convert that Laplacian operator to polar coordinates. Without actually going through the math, that form of the Laplacian operator is shown here. You can see it looks a little bit more complicated, but it allows us to capture the full symmetry of a circle and will make things easier for us in the end. In the other model systems that we've looked at, remember that the energies came out quantized because the wave functions had boundary conditions. For example, for the particle in a box, the boundary conditions were that the wave function had to go to 0 at the edges of the box. For the particle on a ring, something similar will happen. There will be quantized energies because the wave functions have boundary conditions. But what are those boundary conditions? I'd like you to think for a few seconds about that. For a particle moving around a ring, the wave function is going to have a certain value at every point around that ring. So once the object has gone all the way around the circle and gets back to where it started, its wave function also has to get back to where it started. The wave function has to be continuous, and it also has to be smooth. So that means our boundary conditions are that once the wave function goes all the way around the circle and gets back to where it started, both its value and its first derivative have to be continuous. In that sense, you can kind of think of a particle on a ring as a particle in a box that wraps around itself. We'll spend the next few slides actually solving the Schrödinger equation for a particle on a ring to find the wave functions, the energies, and the angular momenta. We'll start by finding the wave functions. For a particle moving in two dimensions where the potential energy operator V equals 0, the Schrödinger equation in Cartesian coordinates looks like this. But remember, we'll be working in polar coordinates, so we have to convert the Laplacian operator, the sum of second derivatives, into polar coordinates. We've already seen how to do this. At first, this polar form of the equation looks more complicated, until you remember that on a circle, the radius r is a constant. That means the terms in this Laplacian operator that include partial derivatives with respect to r can be ignored. That makes the equation simpler, and leaves us with this. If we rearrange these terms, we see that this equation is basically telling us that the second derivative of our wave function psi equals a negative collection of constants times the wave function itself. This problem should look familiar from situations that we've already looked at. We've seen this same type of problem in other situations where v equals 0, like a particle in free space or a particle in a box, where the second derivative of the wave function has to be a negative collection of constants times the wave function itself. In those cases, and in this case, the wave functions are oscillating. They take the form of sines or cosines or complex exponentials. In this case, we'll write the wave functions as complex exponentials. The wave function psi of some angle phi is equal to a normalization constant times e to the I times m sub l times the angle phi. This new variable m sub l is something that you might have seen in the context of atomic orbitals, and something that we'll continue to see throughout the quarter. Next, we'll take the step of normalizing the wave functions, and because the angle ranges from phi equals 0 to phi equals 2 pi going around the circle, the normalization constant is 1 over the square root of 2 pi. So far so good, our wave functions have this form, but we still haven't really talked about what values this new parameter m sub l can have. This is where the boundary conditions come in. Remember, our boundary conditions say that our wave functions have to be continuous and smooth when we make it all the way around the circle. In other words, the value of psi for angle phi has to be equal to the value of psi for angle phi plus 2 pi. We can then plug our wave function into this equation, and use the fact that when we add exponents, we multiply terms. And we can show that this equation is actually telling us that our complex exponential e to the 2 pi I m sub l equals 1. Euler's formula expresses complex exponentials in terms of sines and cosines, and we can rewrite it in this way. And we can then see that the cosine of 2 pi m sub l has to be equal to 1, and the sine of 2 pi times m sub l has to be equal to 0. In other words, that angle 2 pi m sub l has to be a multiple of 2 pi. M sub l has to be an integer. It can be negative, it can be positive, it can be 0, but it has to be an integer. I realize the steps in that derivation came pretty quickly, so I would encourage you to take some time and make sure you're okay with all of the mathematical steps that we just took. Next, let's find the energies corresponding to these particle on a ring wave functions. As we've seen several times in this course, the measured energy of an object is its eigenvalue in the Schrödinger equation. This is the form of the Schrödinger equation that we saw a few slides ago that takes advantage of the fact that the radius is constant on a circle. We can plug our wave functions into this equation, taking the second derivative with respect to phi. We can then combine the constants, and we find that this collection of constants in front of the wave function psi is equal to the measured energy of the particle. So for a given value of m sub l, and remember m sub l has to be an integer, the energy of a wave function is h bar squared m sub l squared over 2mr squared. Try not to get confused by the different uses of the letter m in this equation. M sub l is a quantum number that has to be an integer, and m is the mass of the object. There are a couple things to notice about these energies. First of all, as has been the case in each of our quantum models, the energies are quantized. Because m sub l has to be an integer, the only possible energies are proportional to integers squared. Also notice that because m sub l can be any integer, negative, positive, or 0, it's possible for a particle on a ring to have 0 energy. So unlike the particle in a box or the harmonic oscillator, the particle on a ring has no 0-point energy. Finally, let's find the angular momentum of these particle on a ring wave functions. Angular momentum is something that we haven't really talked about yet in this course. You may remember from physics that a particle moving around in circles in the xy plane has angular momentum in the z direction, perpendicular to the circle. Like other observable properties in quantum mechanics, there's an operator that corresponds to angular momentum. In polar coordinates, the angular momentum operator in the z direction is equal to negative I bar times the partial derivative with respect to phi. So how do we find the observed angular momentum of our wave functions? It works the same way as other properties in quantum mechanics. We apply the operator, and the observed value is just the eigenvalue corresponding to that operator. So, in this case, we apply the angular momentum operator to our wave function psi. We plug in our wave function, We combine the constants out front, and we find that the collection of constants, h bar times m sub l, is going to be the angular momentum that we observe our wave function to have. Again, remember that m sub l can take on any integer value, positive, negative, or 0. In this case, you can think of positive and negative values of m sub l as representing clockwise and counterclockwise motion of our particle. Before moving on, let's summarize what we've learned about the particle on a ring. Like a particle in free space or a particle in a box, the wave functions are oscillating, and we've represented them with complex exponentials. For continuity around the ring, we find that m sub l has to be an integer. It's a quantum number, just like n in the particle in a box or v in the harmonic oscillator. Because of this boundary condition around the ring, the energies and angular momenta of our wave functions are quantized. But unlike the particle in a box and the harmonic oscillator, zero energy and zero angular momentum are possible. We saw that positive and negative values of the angular momentum refer to motion in opposite directions around the circle. And the last thing that I want to mention is that this new quantum number, m sub l, is going to turn up again in the context of the magnetic quantum number in atomic orbitals. So keep an eye out for that. For the rest of this video, we'll move from the particle on a ring to a particle on a spherical shell, an object traveling on the surface of a sphere. The math gets complicated for this system, so we'll only be outlining how to solve it. But before we do that, I'd like to take a minute to think qualitatively about what we expect the solutions to look like for this system. And I want to do that by analogy to the particle in a box. Let's remind ourselves of some key features of the particle in a one-dimensional box. We found that the ends of the box create boundary conditions, forcing the wave function to go to 0. Because of those boundary conditions, the wave functions are quantized waves of varying wavelength. And each wave function has one quantum number that we called n. We then moved on to the particle in a two-dimensional box and saw some similarities. For the two-dimensional box, we now had boundary conditions in both x and y at the edges of the box. We found that the wave functions were now products of two quantized waves, a function in x and a function in y, and each wave function now had two quantum numbers that we called nx and ny. In this video, we're not talking about the particle in a box, we're talking about rotational motion, and we can build up our reasoning in the same way. We started with a particle on a ring, a particle moving in a one-dimensional path around a circle. We found that again we have a boundary condition, the wave functions have to be continuous at the beginning and end of the ring. This boundary condition forced the wave functions to be quantized waves of varying wavelength. And we found that each wave function has one quantum number that we've called m sub l. Now we're building up to a particle moving on the two-dimensional surface of a spherical shell. And we can make some predictions about it by analogy to the particle in a box. Now that the object is moving on a two-dimensional surface, we expect two different boundary conditions in the two angles in spherical coordinates, a boundary condition in theta and a boundary condition in phi, where the shell is connecting to itself. We again might expect the wave functions to be products of two different quantized waves, one of them in theta and one of them in phi, and we might expect the wave functions now to have two quantum numbers. It turns out that those quantum numbers are the m sub l that we've already seen, and another quantum number called L, which you might also recognize from atomic orbitals. So these are our expectations. Now we'll briefly go through the math. As usual, our goal is to solve the Schrödinger equation. Because we're looking at the surface of a sphere, we want to solve the three-dimensional Schrödinger equation in spherical coordinates. The form of the equation shown on the slide is in Cartesian coordinates, so we need to convert the Laplacian operator to spherical coordinates. The Laplacian operator in spherical coordinates gets pretty ugly. But it becomes simpler when we remember that on the surface of a sphere, the radius is constant, and we can ignore the terms that have a partial derivative with respect to r. Still, this is a differential equation that we don't really have enough mathematical background to solve. But I want to mention briefly what approach we could take to solve it. It really is a similar approach that we took to solve the particle in a two-dimensional box. we assume that the wave functions can be expressed as a product of two variables, phi and theta, and we then split the Schrödinger equation into two separate equations, one of them with phi and one of them with theta, which are easier to solve. While we won't actually go through all this math, we can look at the solutions to the Schrödinger equation and try to make sense of their features. The solutions to the Schrödinger equation for a particle in a spherical shell are called the spherical harmonic functions, and they're given in a table in the textbook. There are several key features of these functions to keep in mind. First off, the part of these functions that vary in phi are exactly the same as the particle on a ring solutions that we've already found. They're oscillating functions that can be expressed as complex exponentials. The part of the functions that vary in theta are called the associated Legendre polynomials, and they're powers of sines and cosines that are well known to mathematicians. Each of these functions have quantum numbers associated with them. We've already seen for the particle on a ring that the function in terms of phi depends on a quantum number m sub l. It turns out that the functions that vary in theta depend not only on m sub l, but also on a second quantum number that we'll call L. The first several spherical harmonic functions are shown in this table. You can see that each one is associated with a value of L and a value of m sub l, and each one can be expressed as a product of a complex exponential in phi and a product of sines and cosines in theta. In principle, we could find the energies of all of these spherical harmonic functions by finding their eigenvalues in the Schrödinger equation. It turns out that for each wave function, the quantized energies can be expressed as L times L plus 1 times h bar squared over 2mr squared. Notice that each of these energies depends only on L and not on m sub l. Also, it's important to know that it's only possible to have certain values of L and m sub l. In all cases, L and m sub l are integers, like all of the other quantum numbers that we've seen. But it turns out that L can only be integers greater than or equal to 0, and m sub l can only be integers ranging from negative L to L. While we're not going through all steps of the math, these restrictions come straight out of the math, and it turns out they have major consequences in terms of atomic orbitals. So what do these spherical harmonic functions look like when we plot them? In general, it's hard to draw pictures of these spherical harmonic functions. Most of them involve complex exponentials, so the value of the wave function is actually a complex number. But in the cases where m sub l equals 0, the value of the wave function is real in all places. For the spherical harmonic functions with m sub l equals 0, these pictures show the sign of the wave function on the surface of a sphere. The colors gray and blue are used to represent positive and negative signs of the wave function. Notice that as theta, the angle from the vertical axis, changes, we see more and more nodes as the value of L increases. When L equals 0, there are 0 nodes. When L equals 1, there's 1 node. When L equals 2, there are 2 nodes, etc. So that gives you a sense of what some of these functions look like. You may notice that these spherical harmonic functions are starting to resemble atomic orbitals. That first picture that has 0 nodes looks like an s orbital. The second picture that has 1 node looks like a pz orbital. The third picture that has 2 nodes and sort of has a donut going around it looks like a dz squared orbital. This is not a coincidence, and we'll talk more about this later. The last property of these spherical harmonic functions that I'd like to talk about is their angular momentum. From classical mechanics, the energy of a rotating particle is capital L squared over 2mr squared, where capital L is the angular momentum of that rotating particle. As we saw a couple of slides ago, a particle on a spherical shell with quantum number L has an energy L times L plus 1 times h bar squared over 2mr squared. If we put these two pieces of information together, we can find the magnitude of the angular momentum of a particle on a spherical shell. For a quantum number lowercase l, the angular momentum equals h bar times the square root of L times L plus 1. So let's think about what we know about the angular momentum of a particle on a spherical shell. As we just saw, the total magnitude of the angular momentum is h bar times the square root of L times L plus 1. Earlier, when we talked about a particle on a ring, we found that the z component of the angular momentum equals h bar times m sub l. Let's put all of this information together visually. Suppose a spherical harmonic function has lowercase l equals 2. That means the magnitude of its angular momentum would be h bar times the square root of 2 times 3, or h bar times the square root of 6. That means that if we think of angular momentum as a vector, the angular momentum of this particle is a vector that's pointing somewhere on the surface of a sphere with radius h bar times the square root of 6. If we were to also measure the z component of the angular momentum, we know that its value must be h bar times some integer ranging from -2 to 2. So -2, -1, 0, 1, or 2 times h bar. In the picture on the right, we can see what the angular momentum would look like as a vector. It would have to lie on one of those circles, where we know both the total angular momentum and the z component of the angular momentum. Notice that there's kind of a strange implication of this picture. It means that it's possible to know the total angular momentum and one component of the angular momentum simultaneously, but not more. In other words, if we measure the z component of the angular momentum, then we know that component. But if we subsequently measure the x component of the angular momentum, we then know the x component but no longer know the z component. We talked about this early on in the course, the idea that if you measure one property in quantum mechanics, you can no longer know the value of another. Also notice that this picture on the right illustrates why the absolute value of m sub l can't be greater than L. If it were, that would mean the z component of the angular momentum was larger than the total magnitude of the angular momentum, which isn't possible. Finally, let's briefly summarize what we've learned about a particle on a spherical shell. We learned that the wave functions for a particle on a spherical shell are called spherical harmonic functions, and each one has two quantum numbers, L and m sub l. L has to be an integer that's greater than or equal to 0, and m sub l has to be an integer ranging from -L to L. We learned that both energy and angular momentum are quantized, and they both depend only on L. Also, it's possible for a particle on a spherical shell to have 0 energy or to have 0 angular momentum. We learned that the z component, or any component of the angular momentum, is also quantized and depends only on m sub l. You may already be starting to recognize these quantum numbers L and m sub l from atomic orbitals, and we'll definitely see them again soon when we start to talk about the hydrogen atom. That's all for now. In the next video, we'll talk about some of the implications of what we've learned about vibrational and rotational motion in spectroscopy.